Today, I'd like to talk about a concept called absolute convergence. There's a reason that I've split this off from the alternating series part, because in the alternating series part, you wrote a sub n and meant positive numbers only. And in what we're going to do today, that's no longer the case. So it seemed to me to be confusing. To get started, we need to know some facts. One of them is called the Triangle Inequality, which says if I add up some numbers and I take the absolute value of the result, that can't be any bigger than the sum of the absolute values of the numbers separately. Secondly, suppose you've got a sequence of numbers b1, b2, b3, all of which are positive. The infinite series based on the sequence b sub n converges to some positive real number b. I'd like to split that sum up into two chunks, but I have to make sure that what I'm talking about makes sense. How do I know that the sum n equals k plus 1 to infinity of bn converges to anything? It's because that's the same as the original B series with the first k terms set equal to 0. As we've seen, changing a finite number of terms in an infinite series doesn't change whether it converges or not. So it is legitimate to split the infinite series up into these two chunks. If you do a subtraction, you find out that what you get by starting with bk plus 1 and then adding bk plus 2, then bk plus 3, and so on, must be capital B minus the sum n equal 1 to k of bn. This, though, is a partial sum for the infinite series based on the b numbers. Write this equation down and take the limit as k tends to infinity. In this limit, b, capital B that is, has no k in it. B is a constant. This is a partial sum of the infinite series that converges to b. So both of those limits individually exist. This is b minus b, which is 0. If I start adding an infinite series at some particular index and see what I get, and then I let that beginning index get arbitrarily big, the limit of these sum of ending numbers, if you will, is 0. For emphasis, if I start at 1 and add up all the b numbers, this converges to some particular real number, capital B. If I start at b2, that sum converges to something, but it's not capital B, it's capital B minus little b number 1. This converges to something. Just keep going. You'll be thinking in general about starting with some term and then adding all subsequent terms to it. And as you continue letting the beginning index be bigger, these quantities that we're calculating approach 0. This is going to be very important in a certain thing coming up. Now, suppose you have an infinite series, the sum n equal 1 to infinity an. Unlike what happened in the first half of this section of the textbook, I am not assuming the an's are all positive. They need not be. Some of them could be positive, some negative, some could even be 0. It can change its nature as you go down the list. It is irrelevant. We're going to make a new series out of this. Instead of adding up the an's, we're going to add up the absolute value of the an's. And one question that a person could think is, Is there any guaranteed connection between the convergence or divergence of one of these series versus the other one? Suppose, for instance, that I know somehow that the original series, the sum of the ANs, converges. Can I say without any doubt that the sum of the absolute value of ANs converge? And the answer to that question is no. For example, think about the alternating series version of the harmonic series, which is 1 minus 1/2 plus 1/3 minus 1/4. This is an alternating series that we have looked at previously. But if you take the absolute value of the terms before you add them up, those powers of -1 to the n plus 1, each of them is either 1 or -1. And when you take the absolute value of those numbers, you get 1. The absolute value version of the series that we started with is 1 plus 1/2 plus 1/3 plus 1/4 and so on, which diverges because it's a piece series with p equal 1. So if somebody told you, I've got some infinite series and it converges, so that automatically tells me the absolute value version converges too, that's not a reliable statement. On the other hand, do the same kind of thing, except have n squared on the bottom. This is an alternating series. Terms are positive, decreasing, and approach 0. So that certainly converges. Again, when you take the absolute value version, the powers of -1 are all 1 then. The sum n equal 1 to infinity, 1 over n squared, converges because it's a piece series with p equal 2. So here, there is an example of an infinite series that converges, but the absolute value version doesn't. There's an example where an original series converges and the absolute value does converge. So I can't make any statement like, if all I know about a series is that it converges, then its absolute value series version acts. I have no way to finish that sentence. I can't definitely say it converges. I can't definitely say it's divergent unless I know something more specific about that particular series. So if somebody tries to say something like this, that's invalid logic. It's no good. It's not reliable. I'm not saying that the absolute value series doesn't converge. I'm just saying this line of reasoning is no good. If a line of reasoning that's a conditional is no good, then its contrapositive is no good also. So you can take the logical contrapositive and you'll find out the second statement is true. My previous sentence was a misstatement. These two things are shown to be invalid because of the two examples we just did. This statement is the logical contrapositive of that one, and this statement is the logical contrapositive of this one. But at least we can make certain things obvious as incorrect logic. If you start off, if the sum of the ANs converges then, and you try to say anything about that series, your logic is wrong. If you say the sum of the ANs converge, then again, you can't say anything about that series. The contrapositive of this one is if the absolute value series diverges, then the original series diverges. This statement is logically equivalent to this statement. This one is an invalid chain of logic. This one is an invalid chain of logic. And if you take the contrapositive of this second statement here, you get the third one. These are lines of reasoning that are no good. But there is something you can say. This statement, if the absolute value version of the series converges, then the original series converges as well. It's going to turn out that that is a valid line of reasoning. The reason for it is a little tricky and complicated, so we need to think about this carefully. The premise, which is going to be my underlying premise for the rest of this little argument, is suppose that the absolute value series converges. That's my only assumption. Everything else will be figured out from that. Now, this isn't necessarily only true for terms out of a sequence. What I'm about to say is true for any real number. If you give me a real number, an in this case, it can't be bigger than its absolute value. It also can't be smaller than the negative of its absolute value. And the reason for this is if an is positive, you get an equality on one of these. If an is negative, you also get an equality. For example, suppose that a number n was 7. Then absolute value of that would be 7. Negative of that would be -7. This inequality would read -7 is less than or equal to 7, which is less than or equal to 7, which is true because 7 equals 7. Suppose a sub n was -7, then the negative of that would be 7. The absolute value of -7 would be 7. So you would have a strict inequality here, -7 less than or equal to 7. On the other hand, absolute value of -7 is 7, and the negative of that would be -7. If an were -7, this part would read -7 less than or equal to -7, which is true, and the whole inequality would read -7 is less than or equal to -7, which is less than or equal to 7, which is true. And of course, you get equality all the way across if an were 0. So this is true for any number that you would pick. You don't necessarily have to call it a number n. Having figured this out, add the absolute value of an to all numbers. Here you'll get 0. Here you'll get an plus absolute value of an. And here you'll get absolute value of an plus itself, which is 2 times absolute value of an. Now, we are assuming that the infinite series based on absolute value an converges. So the sum of these things converges to twice whatever this sum converges to. On the other hand, I have a 0 here. 0 is less than or equal to these things, which are less than or equal to the terms of a convergent infinite series. And if you remember the direct comparison test, that says the sum of the things in the middle converges. Now, it's a little hard to see where we're going with this and why we're going down this road. The answer to that is we have to. Remember, infinite series are limits, and when I split stuff up, I've always got to wonder about whether the limits exist or not. So to summarize, the sum n equal 1 to infinity an converges. It exists as an actual real number. This is perfectly valid. If somebody says, I've got an infinite series and the absolute value version of it converges, then the original version converges too. That's 100% guaranteed. The contrapositive is if the original series diverges, then the absolute value series diverges as well. This is less useful than the first one, but it is a valid line of reasoning. Before we talked about this, we had the idea about sum of an converging or diverging. Now, in relation to this absolute value series business, if the sum of the ANs converge, that tells me nothing about the sum of the absolute value of the ANs. But we've just found out something different the other way around. If the infinite series based on absolute AN converges, that is enough to say that the sum of the ANs converge as well. So if people wanted to be more transparent about what they were doing, they would call the first kind, the kind that we're used to, they would call it ordinary convergence, or weak convergence, or conditional convergence. It's that last part that sticks. If a series converges, but its absolute value series doesn't, we say that the series converges conditionally. But the other way around is stronger. If the absolute value version converges, that is enough to say the original version converges as well. The name they should have given that would be strong convergence, or superior convergence, or absolute convergence, which is the name people actually use. So we say that the sum of the ANs converges absolutely when the sum of the absolute ANs converge. That's a strong enough condition to prove that the sum of the ANs converge, but if that's all there were to it, this wouldn't be very worthwhile to pursue. Why is this new thing important to us? To answer that question, I first need to think about what's called a one-to-one correspondence. What I mean by that is this. Write down the kind of indexes that you usually see on the terms you're adding up. So usually we start at 1, so 1, 2, 3, 4, 5, 6, and so on. I'm going to make another column of numbers. In the second column, I'm going to write down positive whole numbers, and the only restriction that I'm going to put on how to write them down is I only write each whole positive number once. So for instance, I might write 38, meaning there is no 38 later on the list. Next, I might write a 6, meaning there's no 6 further on the list. I might write down 210, which doesn't show up any later, 40, which doesn't show up any later, and so on and so forth. My only restriction is every positive whole number shows up somewhere on this list. This is what people call a one-to-one correspondence between these numbers and these numbers. I'm going to make up a special name for these numbers. The number that corresponds to n equal 1, the 38, I'm going to call that J1. The number that goes with 2, the 6, I'm going to call J2. Number that goes with 3, which is 210, is going to be J number 3, and so on and so forth. J number I is the index on this second column that corresponds to number I over in the first column. If you think about making partial sums based on these indexes, doing it the usual way, you would have A1, you would have A1 plus A2, you would have A1 plus A2 plus A3, and so on and so forth. I'm going to use the letter SK for these partial sums. On the other hand, I could use these indexes. The first index is 38, so I'll write down A number 38, which is A number J1. I could write A number J1 plus A number J2. J1 is 38 and J2 is 6. That would be A38 plus A6. For the third of these partial sums, I could have J1 and J2 and J3, which are 38 and 6 and 210. And I could continue doing this as long as I wanted to. It's worth mentioning, sooner or later in this column, I'm going to see every index that's shown up in this column. If I wanted to find A number 38 plus A number 6 plus A number 210 as related to A number 1 plus A number 2 plus A number 3, somewhere in this list of numbers is index 1. Now, that may happen early on, or it may happen very late, but sooner or later, number 1 shows up in the second column. So maybe it's 1,000 or something. Maybe I have to add up 1,000 of these things before I get a number 1. Somewhere on this list is going to be the number 2. It may not show up for 10,000 or 50,000 or 1,000,000, but sooner or later, the number 2 is going to show up in this second column. Somewhere in this column is the number 3. Now that might not happen for n equal 10 million, but sooner or later, the number 3 is going to show up. In these partial sums that I'm building up over here, if I crank the index up big enough, the number 1 will be on the list of indexes. A1 will be in here somewhere. If I crank the index up big enough, but only to a finite extent, the indexes 2 and 3, corresponding to A2 and A3, will show up in one of these partial sums. If you give me A1 through AK, if I crank the index up big enough on one of these partial sums of the R numbers, amongst other indexes, there will be 1, 2, 3, 4 out to K. Now, if what I just said has any mysterious part to it, you might want to think about that real hard, because this is what's going to make everything work for us. So partial sum SK, which is A1 plus A2 out to AK, is a partial sum of the series that we started with, which we are assuming is absolutely convergent. R number K, though, is A number J1 plus A number J2 out to A number JK. It's a sum of K of the A numbers, but the indexes are not necessarily 1, 2, 3 out to K. They could be practically anything. Here's a claim. If the original series converges absolutely, then any rearranged series also converges. Not only that, every rearrangement converges to the same number that the original series converged to. This is important to us. This is going to say if I've got an absolutely convergent series, then I can mess with it the way I mess with ordinary algebra. I can use associative laws and distributive laws if I feel like grouping all of the even index terms together and later grouping all of the odd index terms together. I could do that if I wanted to, and it won't make any difference. This absolute convergence business will let us get away with pretending that we're just doing ordinary algebra. So this is a pretty big claim here. So we need to think about why this is true. So suppose that the sum n equal 1 to infinity an converges absolutely. I'm going to pick a letter k and write down the partial sum that goes with it. I'm going to look at a partial sum for the rearranged series, but it's probably not going to have the same number of terms as sk. So I'm going to look at our number L, which is aj1 plus aj2 out to aj number L. The L is going to be bigger than k, and I'm going to pick it so big that 1 is one of the numbers j1 through jl, and 2 is one of these numbers, and 3 is one of these numbers, all the way out to k being one of these numbers. This means is a subset of. The reason that L has to be at least k is the set of indexes that go with the L are J1, J2 out to JL, and amongst those indexes are 1, 2, 3 out to K. So the very smallest L could conceivably be, if I actually want to do this, is K, and likely it needs to be bigger than that. Now, I'm going to use very informal language here because if I don't, the notation will get out of control. I'm going to look at the absolute value of RL minus SK. Now, SK is A1 plus A2 plus A3 out to AK. RL is the sum of a bunch of the A numbers, amongst whom are A1 and A2 out to AK. When I subtract these two things, A1 cancels out, A2 cancels out to AK cancels out. Even so, K and L are both finite numbers, so if you take what's in common between them out, the absolute value of RL minus SK is equal to the absolute value of the sum of a finite number of these A sub n terms, with n being bigger than k. Why do I say n bigger than k? Because n equal 1, n equal 2, out to n equal k canceled out when I did this subtraction. Then the triangle inequality says that this quantity itself can't be any bigger than the sum of a finite number of absolute value of an A number with n being bigger than k. If I add more terms, more absolute value terms in, I see that RL minus SK is less than or equal to the sum n equal k plus 1 to infinity, absolute AN. And how do we know that converges? We talked about that earlier in this discussion. Also, we pick the L to be so big that the rearranged terms contain within them A1 through AK. L is bigger than K. If I let the K tend to infinity, that's going to make the L tend to infinity also. So take the limit of both sides as K tends to infinity, which parenthetically makes the L go to infinity also. This is less than or equal to this limit. The sum of the absolute value of the ANs converge. So by the thing that we talked about at the very beginning, this limit is 0. In case you forgot the argument, I reproduce it here. So based on this, the limit is K tends to infinity, which parenthetically makes L go to infinity also, of the absolute value of RL minus SK is less than or equal to 0. But on the other hand, all of these absolute value quantities can't be negative. So this tells me that 0 is less than or equal to this limit, which is less than or equal to 0. There is only one number that's between 0 and 0 in this inequality sense. This means that the limit of absolute RL minus SK must be 0. And early when we were talking about limits, we said if the limit of the absolute value of something was 0, that means the limit of the thing itself is 0. We're almost done. I'm going to think about two limits. I'm going to look at the limit of RL minus SK, which we've just shown to be 0, plus the limit as K tends to infinity of SK. Both of those limits exist. This exists because we've just shown it was 0. This exists because the sum of the ANs converge because the AN series is absolutely convergent. That means it's legal to put these two limits together, and RL minus SK plus SK is RK. So I'm not assuming anything when I write limit as K tends to infinity of RL is 0 plus the sum of the original series. But see, RL was AJ1 plus AJ2 out to AJL. If you take the limit as K tends to infinity, that's the same as taking the limit as L tends to infinity, because L is bigger than K of RL. That would be the sum n equal 1 to infinity of a j number n. And what we have figured out is that the original series and the rearranged series add up to the same thing. And again, I want to emphasize when I say rearranged, I don't mean just rearranging 10 terms or 50 or a million or a trillion of them. You could rearrange an infinite number of terms in one of these absolutely convergent series, and it wouldn't change the fact that it converges, and more remarkably, it wouldn't change the thing that it converges to either. This is going to let us get away with a lot of stuff in the rest of this chapter. Based on this absolute convergence idea, we're going to have one more pair of convergence tests, and then we'll be ready to start talking about what we're really interested in. So coming up next is the root and ratio test.